All right, welcome back. We're going to talk a little bit today about a different data type than we've seen before. And this is a data type that was added to VHDL as a way to handle some of the problems with early VHDL designs. The data types that we have already discussed that are part of the standard are actually quite good. They cover most everything you could possibly need. There was one very important omission, and that's one of the things that this new data package that we're going to talk about addresses. Specifically, we're going to be talking about the the Standard Numeric Package. It's an IEEE package that solves one of the big problems that we had early on, and that was if you want to treat a value as, a grouping of signals like a bus as both a value and a vector, it was very difficult. You could create a standard logic vector, which was like an 8-bit bus or a 16-bit bus. And then when you did that, you could access the individual bits of the bus, transfer them to one part of the design or the other, but you really couldn't treat the elements as a value by itself. You couldn't say take an 8-bit standard logic vector, add the value 8 to it, and then hope to get some sort of answer, because standard logic vector isn't about a value, it's a grouping of independent signals. And so adding numbers together made no sense from that standpoint. So the integer data type is designed to handle things that deal with values. So you would use integer if you were saying incrementing a counter or doing something like that instead of a standard logic vector. There are numerous cases though where it's nice to be able to switch back and forth between treating a signal as both a vector and a value. And to address that issue, early designers would create these conversion functions. So they would have a conversion function that would convert an integer to a standard logic vector, and then a standard logic vector back to an integer. But here's the problem. Since it wasn't addressed in a standard, you got a wide variety of people using a wide variety of tools for doing conversions. And one of the key things that I like to stress in this class is we do not want to nail ourselves down to one particular company's products. We want to keep this standard open. We want to be able to shift from one vendor to the next without problem. And because there was no standardized conversion methods, you would start with, say, vendor A, use their conversion function, and then if you ported to another vendor, inevitably they would have a different vendor or conversion function that was not compatible with the other company's conversion function, so it led to some really big issues. The standard numeric package, though, addresses that with a standard new data type, and therefore you don't need those conversion functions and really shouldn't use them if you want your designs to be universally standard among all different vendors. So here's what had happened. When we did this, when they went to the standard numeric package, they solved the problems that were a result of the standard logic vector, and then the problems dealing with the integer. So this actually should be standard logic vector. Sorry about that. Right here, so that should be vector. So standard logic vector and problems with the integer and going back and forth between them. Basically, it did that by standardizing conversion functions to go between them. But it did more than just that. It actually created a data type that could be used in multiple ways simultaneously in your design. So let me show you the best way to see that is to do some examples. So let's run off to take a look at some of those. So first off, let's address the data types. The two new data types are unsigned and signed, and they should be pretty self-explanatory to anybody who knows digital. When you represent a grouping of bits, you can have that grouping represent a number, and if you do so, you have to decide beforehand, am I talking about a signed value or an unsigned value before you can actually interpret the value itself. As you know, an unsigned value is a different range. For instance, an 8-bit unsigned value would have a range of 0 to 255 as far as its allowed values. And an 8-bit signed number would have a range of -128 to +127. So that's just the nature of signed and unsigned values. So the standard numeric package created these two types, signed and unsigned, so that you could address that. You could treat them as one or the other in your design and do computations based on it. Basically, when you declare a signed or an unsigned value, you do so in a very similar way that you would when you declared a standard logic vector. So you'll notice down here we've got two examples. We've got a declaration of an unsigned value, and it uses the same type of notation where you have this is your 7 down to 0 to indicate that you have a range of bits and you've given the bits the number. And so this is an 8-bit unsigned value. The reason we specify it this way is because we can access unsigned values, individual bits or subvectors inside there, just like you could with a standard logic vector. But the advantage here is you can also do operations on this value without having to go through any special conversion functions. So that's really a nice addition to the standard. So let's take a look then at the other one. We have signed as well, so it's declared almost exactly the same way, except you use the word sign, and you give it a vector size as well. So these are just two examples. In order to do this, in order to use the signed and unsigned values, though, you must include a library called numeric standard. Okay, so numeric _ standard. Be very careful. There's a lot of companies that will provide these libraries, and they're vendor specific, so they'll rename them in a confusing way. They'll call them standard numeric, and so that's not the same as a numeric standard. So watch for that. Make sure you're using the IEEE standard library and the standard library names to make sure you're doing this proper. Now, one of the nice things about these two types is not only can you treat them as a vector and a value, but you can also convert using simple conversion function. I mean simple too. This is almost like typecasting in a higher level language like C. It's a very, very easy way to go about transferring from one type to the other in your design. So let's take a look at some examples so we can see how this works. Now, we're going to show examples using unsigned, but you can do this with signed values as well. There's no restriction one way or the other. So since we're looking at unsigned values, let's take a look at kind of a strange example, but I think it kind of makes the point about how to do all of this. So what we're going to do is we're going to draw a little diagram of what's going on here. Basically, this circuit right here is simply doing a addition of a value of 16 to a standard logic vector value here. Okay, so we come in with some value, standard logic vector, and then we want to come out with an adjusted value. So you can think of this as a design where your input is basically going to be value, and then obviously the output will be adjusted value. Okay, and because of that, we need to convert these. Now these are standard logic vectors, not unsigned. So inside the box, inside here, is where we do the magic. And the way we can do that is pretty easy. We can use a function to convert a value into an unsigned value. And so I've done that right here. Let's take a look at this line here. Oh, first off, we have created, so note that, we have created right here some signals for unsigned storage. So we've created a local signal called old value and a local signal called new value that we're going to use when we translate from one to the other. So in this particular case, we're going to be assigning this new unsigned signal called old value the value of the standard logic vector. And we're going to do so by simply doing unsigned in front of it. So this, you use the keyword unsigned, put it in parentheses, and give the value of the standard logic. So it's converting a standard logic vector into an unsigned value simply by doing this particular instruction. So that's kind of nice for that. So let's take a look then at what's happening afterwards. So that's the old value. Old value is a, like we said, is now a unsigned value. And so we can take the unsigned value, that should be old value, not old limit, and add 16 to it. So if we add the value of 16 to it, then that becomes a different number. But we couldn't do that with standard logic. You can't add a value to standard logic vector, but we can with unsigned. And then it works out just fine. So now the new value is an unsigned signal. And then you can take it and convert it back to a standard logic vector by using the standard logic vector, the standard logic vector function here provided by the numeric standard library. So this is a conversion function that converts a unsigned value back into a standard logic vector and assigns that to the adjusted value. So if we draw this out graphically, we can, maybe that will help clarify it for some. Let's start off inside the box. Then we have a port called value that's coming in, and that's our standard logic vector. Now when we come in, we're going to convert that signal, and I just like to draw this as a way to signify a conversion, because I'm basically not changing anything. I'm not putting any logic in here. I'm just changing the type. And so this now becomes the what we call the old value. And then we run it into our equation here, our function. Okay, we can just call that, for lack of a better word, add 16. And so that will take that and add 16 and then write a new value to new value. And then we go through another conversion function, and then it becomes adjusted value. So the numeric, basically what we have here is these are unsigned values, okay? These, let me use a different color. That can really help things a little bit. These are standard logic vectors. And so this little signal here represents a conversion from one type to the other. We're not really creating any extra hardware or anything. We're just redefining what this signal means. And we can use that in unique ways in our design. So all of this goes together to just add 16 to that standard logic vector. You could have started with unsigned and just operated on unsigned, and we're going to talk about that in just a second, about what's a good idea, when to use it, and when's it not a good idea to use it. You'll find a lot of people will use the unsigned function simply to do an operation without really changing the type, and you can use that. And it's a little more complex, but let's take a look at how that might work. So what I'm going to do is I'm going to just take this little stuff and let's shrink it down for us. Don't want to quite get rid of it because it does kind of show relationship here. But I do want to rewrite this. So without doing all of this and creating the intermediate signals, there is another way to approach this. So we can do this by simply doing a conversion, adding, and then reconverting it back. So follow me here. If you don't understand, that's okay. You can do it the other way. But I like to show this because it does show a common way that people will use signed and unsigned to do math quickly and then get right back to the standard logic vector notation. So what we could have done is we could have said adjusted value is assigned, and now we know adjusted value is a standard logic, right? So that needs to be standard logic vector, and we're going to put that as part of our function. But we need to first off convert it to an unsigned, so then we can just basically do unsigned value, add 16 to it, and then convert it back to a standard logic vector. So let's follow that real quick so you can see what's going on here. Basically what's happening is we're taking our input value, we convert it to an unsigned value, add 16 to it here, okay, and then convert it back to a standard logic vector, and now it just gets that assignment there. So that greatly simplifies the problem as far as writing it out, but it can be confusing if you're not familiar with this type of technique in writing the code. So this is something you'll probably see a lot if you're looking at other people's code and when they need to do addition and stuff. So it's a nice little, not really a trick, but it's a nice little way of doing notation. Two possible ways of addressing the same issue. All right, so the next one is how do you treat it as a vector? And so here's a good example of that. We have two unsigned values that have been declared in our design. There's switches and then there's a nibble swap. Now nibble, remember, is a 4-bit value. So if we've got an 8-bit value, a byte, and we want to swap the nibbles, that means we're going to take the upper and lower 4 bits and kind of swap their position in the vector. Just like we would with any vector, we want to be able to shift the values around. And we can do that by simply doing a statement like this, where nibble swap is assigned switches 3 down to 0, ampersand, that's a concatenation operator, with switches 7 down to 4. So we've done a swap and we've assigned it and we've treated it like a vector. So like we said before, unsigned or any of the unsigned or signed data types that come with the numeric standard, we can treat them as a vector and we can treat them as a value. Now that we've said that you can treat them both as a vector and a value, you're probably wondering, well, why not make everything unsigned and signed, and that solves all the problems? And that's really not a great idea. You'll find that the necessity of using signed and unsigned is actually quite limited. You don't really need to use it a lot. If you come from a language background where you program in higher level languages, it's uncomfortable to think in terms of hardware and think in terms of vectors and that kind of thing. So it's understandable that people might want to fall back on the signed and unsigned as a tool that just does it all. But it's really not a great idea because it is somewhat limiting, especially when you consider that using an integer can be an incredibly beneficial part of a VHDL design, because it doesn't really limit you to the number of bits. You don't even need to worry about it. Let's say you have a series of data that you want to read in, and there's 532 bytes worth of data for whatever reason, and you want to create a way to count through that. Well, you could go through and try to compute how many bits that would be, and then how big a vector you would need to have that bits, or you just declare an integer that goes from 0 to 532 or whatever the number was I said, and that will cover it for you. So I find that I use unsigned and signed 1% or less of the time in my designs. It's almost never used except on certain occasions where it's beneficial. Most of the time, integer and standard logic vector will work out fantastic, and you don't really need any of that other stuff. So I encourage you to not use the numeric standard types unsigned and signed unless it really benefits your design for some reason. Obviously, if you're creating let's say an ALU unit inside your VHDL module, right, you would definitely want to use signed and unsigned, because that actually makes the job of creating an ALU easier, because it does both bit manipulations with shifts and the like, and also computational things like adding and subtracting. So it just fits. That's perfect. But most of the time, you're not going to be doing that kind of thing in your design. And it might actually stray you away from using better practices like standard logic vector and integer. So standard logic vector and integer, most of the time, that's what you're going to use. Numeric standard is there to help you when you really need that functionality. I find I tend to use these more in test benches, honestly, than actual synthesized designs. But they can be useful, and you need to know about them. And that's why I think it was important for us to have this video. So hopefully that's helped you kind of get up to speed. We'll see you next time in the next video. Thank you.